Hello and welcome to this video that goes through the Physics and Maths Tutor Motor 1 questions. Question 1. Figure 1 shows a straight wire passing through a piece of card. Current is passing down through the wire, and describe how you could show that a magnetic field has been produced around the wire. So in this one, we're going to use the right hand rule. Why do we use the right hand rule? Well, the right hand rule is all to do with so a current carrying wire is passing down here, and this will generate or induces a magnetic field around it. So as the current passes through the wire, there's a magnetic field around it, and this is essentially where this comes from. So any wire will have a magnetic field around it as long as that there is a current. And the right hand rule simply states that your thumb acts in the direction of the current, and then you curl your fingers into a fist, stick your thumb out in the direction of the current, and the curl of your fingers equals the direction of the B field. So in this situation, you've got the current that's going down, and the curl of your fingers should go around in a clockwise direction. So it should be in this direction of the magnetic field. Now, it doesn't quite relate to this question because you could describe how you could show that magnetic field has been produced. So to show that, there's two possible ways that you could show a magnetic field has been produced. One, you can use a magnetic compass. So use a magnetic compass and place it around the wire. And then what you want to do is you want to record the direction of the needle every time you place it. So you end up drawing the magnetic field around this one, because the needle, every time you place the compass down, the needle will change direction, so you could put an arrow to point in that direction, so you would end up with something maybe like this, and that will show you the direction of the field. So that's answer 1, and that's 2 marks. Or the second one, maybe a bit easier, is to sprinkle some iron filings or another magnetic material. Iron probably the easiest one. So sprinkle some iron filings, and if you place a magnetic object inside the magnetic field, and then if you move that object, then the object will fall into the magnetic field. So if you place lots of iron filings all around the card in a random order, and then you move those filings, so then you need to tap the card. So you should be specific in your answer. So sprinkle some iron filings around the card. If you tap the card, then the iron filings will show the pattern or show the magnetic field. Oops. And that's it for question 1 and 2. As in not for different questions. So that's either 2 ways you can answer this question. So part 1, compass, part 2, or another one is iron filings. Again, say exactly what you're going to use and then how you're going to use it and how that shows the magnetic field. Okay, figure 2 shows the ignition circuit used to switch the starter motor on in a car. To switch the starter motor in a car on, the circuit uses an electromagnetic switch. Explain how the ignition circuit works. So this is quite a difficult question. So to see the setup here, we have a circuit that starts on the battery, goes around here. We will turn the switch on. So the first thing that you're going to do is turn the switch. So close the ignition switch. Again, something like this is easy to miss out, but you might not lose a mark if you don't mention it. You might still get full marks, but it's an easy way to gain a mark and start your answer off. So close the ignition switch, which allows current to run through the circuit. And rather than saying circuit, let's have a look at exactly what it's going to go. So we turn the switch off, we close the switch, current moves through, and it goes through the electromagnet. So to run through the electromagnet. Okay, and again, the current will go all the way through. Now the electromagnet here has an iron core. So from our previous question, we discussed that a wire generates a magnetic field. If we remember, if you have, for example, a solenoid, which is what this is a solenoid, an example of a solenoid, but this time it's got an iron core inside it. So remember the magnetic field of inside a coil of wire will look something like this, and that's exactly what's happening here, is that there is a magnetic field that is generated when you run the current through the wire. Again, a current carrying wire will induce a magnetic field. It creates a magnetic field. You can think of it like that. And the magnetic field will run through the iron core. Now the iron core, so it turns to the electromagnet. So this then creates this core. Now the iron core is a magnetic material. So the iron core then becomes magnetized. So with the iron core magnetized, that becomes really important because again, there's a magnetic field running through it. So if there's a magnetic field running through the magnetic material, then it becomes a magnetic material with it, and this means that it can attract. So the magnetic field is most strongest at the top here. So it's going to attract this part of the pivot. And the pivot is made out of iron, hence why it will attract it. So the pivot arm above the magnet, or not the pivot arm, we should just say the iron arm. So the iron arm above the magnet is attracted to the magnet. Okay, so that causes this to cause attractive. So if this comes down, then this part of the iron arm is going to go out towards the starter motor contacts. So the other end, or the long end, you could say, be more precise, the other end, or we'll say long end here, of the arm hits the starter motor contacts, and once it's hit the starter motor contacts, so once this is complete here, this pushes the contacts together and this creates a full circuit here. So therefore the starter motor circuit is complete. Therefore current runs through the starter motor. And there we go. And that's your circuit running, that's your starter motor running. Again, make sure you're clear, make sure you follow logical steps all the way through, so it's a clear, like, this event happens, and this event happens, and this event happens, and try and involve as much physics as possible. So the iron becomes magnetized, and this attracts the arm, so try and use as many key scientific content to try and guarantee yourself the 4 marks. But one way to approach this question again is, if you want to shorthand it, just write a quick 1, 2, 3, 4, and then you can write it in full sentences, just so that you don't forget it. So again, whenever I approach these questions, again, I wrote it freehand, but if you're not sure, just go R switch, and then R magnet, and then that pulls the arm, arm attracted, and then that hits the starter contact. So again, so you're just writing quick bullet points down, so that then when you write out your answer, you're not going to forget any part of it. Okay, question 2. This is, describe what happens to the wire X when the current is switched on. And here you've got a horseshoe magnet, bare copper wire, with a plus and minus switch, and in this situation you are wanting to determine the direction of the wire. So this rule, if you've got a wire or a conductor, so a wire is a classic example in a magnetic, will represent magnetic field as B field, then we're going to use the left-hand rule. So the left-hand rule is the force or the direction that the wire will move. Then the way to remember the next one is that first finger is field, and the field is the magnetic one. So first finger, so your index finger, is the B field, and then your second finger, your middle finger, is going to be the current. So whatever the I, the current. Okay, so in this situation, so which way is the magnetic field acting? So the magnetic field is going from north to south. So this, you're going to put your index finger going down. Now the current is the most interesting part here, because the current is going to flow from positive to negative. So current will flow in this direction, so therefore your wire will go to the right. This is because your current will flow going towards it, so positive to negative current direction the current flows, so the wire goes to the right when you do it, because you'll have your middle finger pointing towards you. So the way that you want to set this up is the index finger goes straight down, your middle finger goes towards you, and then you should have your thumb pointing out to the right, and that means that your wire will move to the right. And what difference do you notice if the following change is made? So if the magnetic field is reversed, so if the magnetic field is reversed, that means that your index finger will go upwards, and your current though will still go in the direction of the thing. So if the magnetic field is reversed, actually you don't need to do it with the hand, because the magnetic field is reversed, then the force is reversed. So you just need to say if any of the directions are reversed, then the force is reversed. This one's quite difficult to do with your hand. So you are going to index finger going upwards, current. So you'll have your index finger pointing towards the palm of your index finger pointing towards you. Your middle finger so your index finger is pointing upwards. Your middle finger is pointing towards you, and your thumb will be pointing to the left. So the force is reserved, it goes to the left. If the current is increased, so if I is increased, that means that the force will increase. F is equal to BIL. So if I increases and the magnetic field strength stays the same and the length stays the same, therefore the force will increase as well. So therefore you will have a force increase, so the force, the movement of the force will be, or the force will be larger. So you'll have a larger force, or you could say that the wire moves faster. Sorry, be very slow. But yeah, the force is larger here. Okay, part B. The diagram shows a coil placed between the poles of a magnet. The arrows on the sides of the coil itself show the direction of the conventional current. The arrows labelled F show the direction of the forces acting on the sides of the coil. Describe the motion of the coil until it comes to rest. So here you're going to have the forces are acting on it, and it's acting on as a clockwise direction. so the coil moves in a clockwise direction. And then what it will do, it will oscillate between these, so the motion will oscillate. So it will oscillate and reverse before coming to rest. Facing the field. So what does that mean? So that's a perfect 3-mark answer to this one. What happens is that the coil will go round, so the direction of the coil, so if this is a side-on view of the coil, so that's the part of the coil goes round, and then eventually it will rest so that it's facing the field. So there's the magnet, so essentially it's like this, the magnetic field lines will go through, but it's at 90 degrees to the field, and then that's where it will sit and rest. Unless there's some action that turns the coil round. And then most electromotors use electromagnets instead of permanent magnets. State 3 of the features of an electromagnet which control the strength of the magnetic field. So in this one, an electromagnet, remember, was in our situation before where we had the coils wrapped round. So with the starter motor question, so one thing that controls the magnetic field strength, first of all, is the coil number. So the more coils you have, the better. The core of the magnet. So if you have for example, you can use air, and you can use a iron core. An iron core will have a higher, will produce a higher magnetic field, a stronger magnetic field because it's a magnetic material, while air will still produce a magnetic field but not as high. And then another example could be the current. So the higher the current through the wire will generate a stronger magnetic field. Your other one you could have had is the number density of turns. So if you had lots of turns very close together, then that would also count. But I'd say the easiest ones to remember are coil number, the core of the magnet, and the current. Question 3. When a conductor carrying an electric current is placed in the magnetic field, a force may act on it. State 2 ways in which the force can be increased. So for this question here, we want to use the formula F equals BIL. So the two obvious ones to increase are B and I. So you could say, for example, increase the magnetic field strength. Avoid saying something like stronger magnet, or do never use bigger magnet as well, because a bigger magnet doesn't necessarily mean a stronger magnetic field. You just use the actual correct term. So increase the magnetic field strength is the perfect answer. And another one you could use is increase the current. And you could say that, for example, increase the voltage, etc. That would count, but just saying increase the current is enough to get the mark. It's just saying 2 ways that you can do it. State 2 ways in which the force can be made to act in the opposite direction. So the first one is to change the direction of the current, so the current acts in that direction. To do that, we need to change the polarity. Now the polarity is just is basically all we want to do is change over the wires in the battery. And if you do that, you will get the current flowing in the opposite direction, and therefore your force will act in the other direction. And the other way that we could do this is reverse the magnetic field direction. And that reversing the magnetic field direction will also change it again. You get your left hand, if you flip, for example, the field going from into the page to flip it going towards you, you'll notice that your thumb will change direction. So therefore, that's 2 ways in which the force can change direction. In what circumstance will no force act on a conductor carrying an electric current? So this only occurs when the conductor is parallel to the magnetic field. So by parallel, the reason why is that it doesn't cut any field lines. So if this is your conductor and this is your Y, so this is the wire, and if you have the magnetic field, no, that's not parallel, is it? That's not very good. So you want to show this perfectly. So if it's like this, then there is no force because it doesn't cross any field lines, so therefore there is no force acting on it. So essentially, if they go in the same direction as each other, there is no force acting on the conductor. It will just, it will stay in its position. Question 4. Many electrical appliances use a circular motion produced by an electric motor. Put ticks in the boxes next to all the appliances in the list which have an electric motor. So this one might require some of your own knowledge, but again, just think of anything that has a kinetic motion to it, because that will drive, that's why a motor works, because you've got the magnet, or no, actually you can use a magnet, but let's use a coil of wire inside a magnet, so north and south, and the wire will move and spin, and you can generate mechanical motion or kinetic motion doing this. So a drill would be a good one to use electric motor. A fan, because a fan has kinetic motion to it. Anything that spins, a food mixer spins, and a screwdriver spins. So you can think of anything that spins. There's a good opportunity appliance that will use an electric motor. An iron will not, because an iron just requires heat to conduct, so therefore does not need an electric motor. An electric kettle, like a well, just uses doesn't need anything. It just uses a wire inside that heats up the water. So you should have 4 answers for this one: a drill, a fan, a food mixer, and a screwdriver. Part B, a simple design of electric motor shown in the diagram. It has a coil which spins between the ends of the magnet. Give 2 ways of reversing the direction of the forces on the coil in the electric motor. So again, for this question, you're going to use a very similar answer to the previous one. So if you want to reverse the direction of the coil, you can reverse the current direction, or just reverse the current, you could say, so reverse the direction of current, and you can reverse the magnetic field. Again, it's not asking for how to do that, you just need to be able to reverse it. Give 2 ways in which increasing the forces on the coil in the electric motor. So this one, you could have increase the magnetic field strength, that increases the force. And you can just use the same, very similar, the same one here, increase the current. So increasing the current and the magnetic field strength increases the force, and vice versa for decreasing. And then the next one is you could reverse if you reverse the direction of it, it reverses the direction of the force. There are other options that you could have had. So for example, you could reduce the gap between the coil and the magnets. So that means that you're getting a stronger magnetic field that way. And also you could, if it's this one here, you could have multiple coils, which would generate a stronger magnetic field. It's a better force, sorry, so more coils. It wouldn't increase the field strength, it just increases the, it will increase the current going through, and therefore the thing, so you could use more coils here. However, 1 and 2, the magnetic field strength and increasing the current is probably the easiest ones to remember. Question 6, a student investigates the electromagnetic force acting on a wire, and draw X on a diagram with the centre of the X being the strongest part of the magnetic field. So here, if we remember that a wire has a magnetic field that will go around the wire. So in this case, quite hard to draw, but it goes, imagine that circle is, that if the wire is acting, so if you put your finger, or your thumb even, that's going from left to right across the page, and the magnetic field is acting around it. So it's acting perpendicular at a right angle to the page. So here, the strongest part of it is where the wire is, because that's where the magnetic field strength is, and it's also between the two ones. So you want to put it exactly in the middle, between the north and the south pole. Give one change that you can make to magnets to decrease the electromagnetic force on the wire. So for this one, we could simply just move them further apart. If you move them further apart, then the magnetic field strength decreases. So very much like anything, like two charges together, or moving a mass away from a small mass away from a heavy mass, that will reduce the force acting on it. So here, just increase the distance to the mass. If you're struggling to increase the distance to the magnet, or as you could say, between each other. Now, the reason, if you're struggling to think about it, think if you had like a nail or something and place it near a magnet. If you place it far enough away, it won't get attracted, and if you bring it closer, it gets attracted quicker. Well, first of all, it gets attracted, and then you bring it closer and closer, it gets attracted quicker and quicker. So yeah, that's how it works. So for part C, the student wants to change the electromagnetic force on the wire without changing the magnet's moving position. Give one way that she can increase the electromagnetic force. So if she wants to increase the electromagnetic force without changing the magnets, then you need to do something to this circuit. So to increase the magnetic force, you need to increase the current, which they will accept, but you probably want to say exactly how you're going to do it, since you've got a circuit set up here. So you could say, for example, add more cells to the battery, or you could say increase the voltage, or you could also, for example, reduce the resistance. You've got a variable resistor here, so another option is to say, we reduce the resistance, which will increase the current. But all of these things will increase the current, and therefore increase the electromagnetic force. And then give one way in which you can reverse the direction. So again, this one is reverse the polarity of the battery. And therefore it will reverse the direction of the current. But you can swap it around, swap the connections around the battery. So instead of having the wires come in like this, so if that's 1 and 2, you now have it coming through where this is 2 and this is 1, and that reverses the direction around, so you're just swapping the leads over. Okay, question 7. So a science technician sets up an apparatus below to demonstrate the motor effect. He uses a powerful permanent magnet. The copper wire is placed along the metal rails. When the switch is closed, the copper roller moves to the right. Complete the sentence by drawing a ring around the correct line in the box. This happens because the copper is, and this one is because the copper is an electrical conductor. So again, in this situation, why is it moving to the right? So first of all, you have the magnetic field going downwards. You've got the thing coming out of the page, is the way that you can think about it. So again, using the left hand rule, thumb is force, index is field, so magnetic field, and the middle finger is current. So if you get your finger, then you have the magnetic field going from north to south, so that's going downwards. You put your middle finger pointing towards you, and your thumb will stick out to the right, so the copper roller will move in this direction. And the reason why the copper roller will is because it's an electrical conductor. Suggest one change that the technician can make which will cause the roller to move faster. So essentially, two things is you can increase the current or increase the field strength. Either one will increase the force, which will move the roller quicker. Suggest two changes which the technician can make, one of which will separately cause the copper roller to move to the left. So this one is reverse the magnet. So the magnet is, or reverse the magnetic field. So the magnet, instead of north to south, now north will be at the bottom and south at the top, and that will cause the wire to move the opposite direction. And you can see that if you point your finger upwards, put your current out of the page, you will find that the magnetic field will move to it. So will move to the left instead. So for that one, you're going to have your index finger pointing upwards and facing you, and your middle finger pointing. So you should have basically your palm facing you, and you should see that your thumb will go out to the left. And it suggests two changes. So your second change that you would do is to reverse the connections to the power supply. Because you want to swap over the battery. So for that one, you would you would have that wire there and that wire there, and that will change the direction of it. BI, many electrical appliances such as vacuum cleaners, drills and CD players contain electric motors. Complete the sentence by drawing a ring around the correct box. Generating more electrical power to increase the number of electrical appliances used raises an ethical, environmental or political issue. So if more electricity is generated, electricity produces pollutant gas. So if you have more electricity, you're going to increase the number of pollutant gases. So this becomes an environmental issue. The number of electrical appliances used in the world's richest course is increasing, yet many people in the world's poorest countries have no access to electricity. What type of issue does this inequality between people in different countries raise? So this will raise an ethical issue, because is it ethically right that rich countries continue to use appliances and use more and more appliances while the poorest countries can't, and they don't even have access to electricity? So it's this rich versus poor argument of why can't rich countries support poor countries rather than spending that resources on improving things for them when they're already at a high level. Why can't they use that resource to improve poorer countries? Question 8, which is the last question, complete the description of the box. So here you've got a magnet with a axle, we've got a wires inside of there and a coil, and if it's a coil inside a magnetic field, the first thing you should be thinking of is that it is going to be a motor. So it's not a transformer. A transformer is when you have something like this, for example, or hang on, that's a terrible drawing. So you can have this would be a transformer, an example of a transformer, and you've got wires that are wrapped around and another set of wires are wrapped around. So like step up and step down transformers, for example, change the voltage and use the greater magnetic field, and those magnetic fields interact with each other, and that's a transformer. This one is just a coil inside the magnetic field, so it's a motor. The coil needs a flick to get started, then one side of the coil is pushed by the cell coil or force, and the other side is pulled, so the coil spins. So if it's pushed by a force, and the other side is pulled. So essentially you get it started and then it will run by itself. That's the idea of an electromagnetic motor. So just two changes of the devices which will make the coil spin faster. So this one we could use a stronger magnetic field. So something like a more powerful magnet. And then the second one is there's lots of options for this one. So we could reduce the gap between magnet and coil. We discussed this one earlier. So that increases the magnetic field strength that the coil experiences, because you've got more magnetic field lines passing through between magnet and coil. You can also increase the area, so increase coil area. You can use a more powerful cell, so we've got the cell here, so increase the cell voltage, or you can have more turns, and that will also generate make the coil spin faster. State changes to the device which will make the coil spin in the opposite direction. So again, we're going to reverse the cell or reverse the polarity of the cell. And then the second one is reverse the magnet, so your poles are in opposite directions. And that's it for this set of questions. Any questions, please let me know.